So here's an example of how we can directly apply the second fundamental theorem of calculus. Let's say that y is equal to the integral from 1 to x of 1 over 1 plus t squared dt. We want to find y prime. Well, in order to use the second fundamental theorem of calculus, we want to make sure that f is a continuous function and that the integral that we're taking the derivative of has a constant on the lower boundary and a variable on the top boundary. If all that's true, then we can just plug that top boundary in for the t inside the function, and that would give us f of x. So then for y, our bottom boundary is a constant, 1, so that's okay. The top boundary is a variable, x, that's okay. And the function itself is continuous. So then we can apply the second fundamental theorem of calculus for finding y prime. All we have to do is substitute that top boundary from the integral, the x, in for all the t's inside the function. And that would give us y prime is equal to 1 over 1 plus x squared. Here's another one. Y is equal to the integral from x to 0 of tan of t dt. So have a look at this function defined by an integral and think for a moment, are there any issues? Is there anything here that would stop us from applying the second fundamental theorem of calculus? Have you thought about it? Okay, so there's two things that we have to consider. The first is the function inside the integral continuous? Tangent itself is not a continuous function. It actually has a vertical asymptote every pi. The two vertical asymptotes nearest to 0 would be at negative pi over 2 and positive pi over 2. So that value of x couldn't go beyond negative pi over 2 or positive pi over 2. But as long as x is within that, tangent is continuous. And then the second issue is the boundaries of the integral. To use the second FTC, the bottom boundary has to be a constant, and the top boundary has to be a variable. In this case, the bottom boundary is the variable, and the top boundary is the constant. So we need to flip the order of integration. And lucky for us, there's actually a property of definite integrals that will do that for us. That's the first property of definite integrals that we looked at. We can swap the order of integration by putting a negative out front of the integral. So then we can put an x on the top and a 0 on the bottom if we put a negative out front of the integral. And now we're good to go. We can apply the second fundamental theorem of calculus for this, just as long as x doesn't go beyond pi over 2. So then y prime would be the derivative of our negative integral. We can then factor the negative outside of that derivative so that we can directly apply the second fundamental theorem of calculus. That means our answer is negative tan of x. Let's say that y is equal to the integral from 0 to x squared of cosine of t dt. Notice that top boundary is more complicated than just an x. In this case, it's x squared. Here's how we would solve this without using the second fundamental theorem of calculus. We first evaluate the integral. That means that y is equal to sine of t from 0 to x squared. Plug in the top boundary, x squared. That will give us sine of x squared. And then subtract and plug in the bottom boundary of 0. So we'd have minus sine of 0. Sine of 0 is just 0, so that would leave us with sine of x squared. And in order to evaluate the derivative of sine of x squared, we'd have to use the chain rule. The outside function is sine. The derivative of sine is cosine. Keep the x squared inside of cosine, and then multiply that times the derivative of x squared, which would be 2x. There is a faster way of solving this problem using the second fundamental theorem of calculus. Let's look at our answer and compare that to the original FDBI. In our answer, cosine of x squared, that function is the same function that was inside of the integral, with the top boundary plugged in for t. And then the 2x inside the answer is the derivative of that top boundary. So then, knowing that we're going to have to use chain rule, we can directly use the second fundamental theorem of calculus. So start by plugging the top boundary in for the t. That would give us cosine of x squared. And then just take the derivative of that top boundary. the derivative of x squared would be 2x, and that is our answer. You would have to do this anytime the top boundary is more complicated than just an x. If the derivative of the top boundary is not equal to 1, then use chain rule. So here's a quick example of using chain rule with the second FTC. Let's say if we want to find the derivative of the integral from 0 to x cubed of 3t sine of t dt. So all we need to do is substitute in that top boundary, the x cubed, in everywhere we have a t. That would give us 3x cubed times sine of x cubed. And then the chain rule part would be multiplying all of that by the derivative of the top boundary. So the derivative of x cubed is 3x squared. We can then simplify this as 9x to the 5th power times sine of x cubed. Okay, so there's one other way to make this harder. What happens if both the top and bottom boundaries of the integral are variables? In order to use the second FTC, the bottom boundary has to be a constant. So here's how this works. We want to rewrite this integral as two different integrals that both include at least one constant. And in order to do that, we're going to go back to the properties of definite integrals. So we can use property number 5. If we have an integral going from a to c, we can split that up into two different integrals. The first integral going from a to b, and the second integral going from b to c. So then we can rewrite this integral as two different integrals. The first integral would start off at the lower boundary of x, and it would go to some unknown constant. Let's just call that a. And the second boundary would pick up where the first one left off at a, and it would continue up until x cubed. So in the original integral, the lower boundary was x, so there's our lower boundary of x. The upper boundary was x cubed, there's our upper boundary of x cubed, and we just created some arbitrary constant in between, called it a, and split it into two different integrals. So then this first integral goes from x to a. We need the constant to be on the bottom. And we can handle that by swapping the order of integration. So the first integral would go from a to x, and it would just have a negative out front. The second integral doesn't change. And now we can use the second fundamental theorem of calculus. We can just apply the second FTC to each of these two integrals. That means the y prime would be the derivative of our two integrals added together. Using the second FTC on the second integral, we'd have cosine of x cubed, and then the chain rule part means we'd have to multiply times 3x squared. And then if we just rearrange the terms, that would give us 3x squared cosine of x cubed minus cosine of x. There is actually a shortcut for this one as well. Going back to the original problem, the top boundary of the integral was x cubed. The lower boundary of the integral was x. Well, notice that the first part of our answer, 3x squared cosine of x cubed, is what you would get just by plugging the top boundary in for the cosine and then doing the chain rule. We would then subtract and do the same thing for the bottom boundary. Just plug the bottom boundary in for the cosine. So really all we're doing is using the second FTC for the top boundary, subtracting, and then using the second FTC for the bottom boundary. So here is one last quick example, just using that shortcut. Let's say we want to find the derivative of the integral from 2x to 2x to the 4th power of e to t dt. So in order to answer this, I'm going to use the top boundary. That would be e raised to 2x to the 4th power. We'd have to use chain rule. So the derivative of 2x to the 4th power is 8x cubed. Then subtract and plug in the bottom boundary. The bottom boundary is 2x. That would give us e to the 2x. And then the chain rule part for that would be the derivative of 2x, which is just 2. Rearranging the terms, we would have 8x cubed e raised to the 2x to the 4th power minus 2e to the 2x.